And here we have been asked the number of unpaired electrons which will be present on the central metal. Statement based questions which are coming, and match the columns also, were there. So is more of an electron withdrawing group, both in terms of its power of -I and -m. Followed by that, if you see, this is also deactivating, this is also deactivating. So next will be, so hello students, welcome to Allen Overseas. I hope your preparation for NEET 2023 is going well. Now to enhance your preparation, we have come up with this series which will include 90 most important questions, out of which 30 questions will be there for each subject for this discussion. So if I go ahead, in the case of chemistry, I'll be discussing 15 questions, and so is the case with other subjects. So 30 questions will be there in each of the subject in this series, and today we'll be discussing these 15 questions. Okay, so if I talk about the videos for other subject, the playlist you will be provided for each of these videos, and you can see the link in the description. Okay, so let's start with our today's session when I talk about question number 1. So it says that the correct order of rate of nucleophilic substitution with aqueous NaOH is. So here in this particular question, we are discussing about SNAR, and these are the kind of options which is provided because we are provided with aromatic compounds. So we are discussing nucleophilic aromatic substitution, and we are being asked the rate of nucleophilic substitution with aqueous NaOH. Now, when I talk about that, what is the factors on which my SNAR depends, we'll keep in mind that SNAR, if I talk about SNAR, on what factors it depends. If I talk about, let's quickly discuss that particular part. If I talk about factors which affect SNAR, then the rate of SNAR, it depends on electron withdrawing groups. So more the electron withdrawing groups we'll be keeping, more will be the rate of SNAR. We'll keep that thing in mind, because we'll keep in mind that in SNAR, which is addition elimination, the intermediate which is forming is carbon ion. And to check the stability of carbon ion, we need to have more and more electron withdrawing groups. So the more electron withdrawing groups we have, the higher will be the rate for SNAR. Okay, so now when I see all these options which is mentioned here, I can see that I have been provided with chlorobenzene in all these 4 options, and I need to substitute that with OH because we are provided with aqueous NaOH. Now without these electron withdrawing groups, this task is very difficult, because you know that because of double bond character which is there, between this chlorine and benzene, because you know that chlorine will be in resonance, the lone pair will be in resonance or will be in conjugation with this ring. It is difficult to substitute chlorine, and that is why we need drastic conditions. So in general, we need drastic conditions, but in order to reduce those drastic conditions, we put in more and more electron withdrawing groups. Now, you can see that the highest electron withdrawing groups which we have is 3 in the case of option 3rd. And you know that nitro is a -I -R group. Apart from that, the next which we can see here is option number D, where we have 1 nitro. Followed by that, we have chlorobenzene, where we have no such group present. And lastly, we have methoxy group. Methoxy group is not a supporter. Methoxy group is actually a +M group. It is not going to stabilize my carbon ion. It will actually destabilize it. So methoxy, which is a -I +M group, will not be a supporter in this particular case. Therefore, finally, if I talk about the rate of nucleophilic aromatic substitution, it will be C followed by D, followed by B, and followed by A. And the option which we can see here is second option. So that's your answer for this particular question. Now, moving ahead. Okay, so here we have our question number 2, where we are provided with a match the column. Here you can see this question is of coordination compound, my dear students. And here we are being asked the number of unpaired electrons which will be present on the central metal or the central metal ion in each of these complexes. Now we'll keep in mind here the important thing which we'll keep in mind is the ligands. How ligands are playing a role in deciding the number of unpaired electrons. If there is a strong ligand, obviously pairing will take place, and if in case there is a weak ligand, then pairing will not take place. So based on this concept, we'll be solving this particular question. Now, you can clearly see that chromium in this particular state is in +3. Iron here is in +2. Nickel, if I talk about, it is in +2 and followed by cobalt, which is again in +3. Now, cyanide is a strong field ligand. So, cyanide is a strong field ligand. Water is a weak field ligand. Ammonia is a strong field ligand. And if I talk about ammonia again, it is a strong field ligand. So, strong field ligand will support pairing. Now, here you can see that chromium is in +3 and in +3, it will be a D3 configuration, 3D3. If I talk about iron +2, it will be 4s0, 3d6 configuration. If I talk about nickel +2, it will be 4s0 and 3d8 configuration. And if I talk about cobalt +3, you know that cobalt in general is having 4s to 3d7 configuration. If I remove these 3 electrons, I'll be getting 4s0, 3d6. Now, in the case of cyanide, I will not carry out any pairing of these 3 electrons because in octahedral complex, these will be going straight away in T2G. All these 3 electrons will go like this as it is. So, according to CFT, we'll keep in mind that these 3 electrons will go as it is. Number of unpaired electrons will be 3. If I talk about this particular complex where here iron is having 3d6 configuration, will pairing will take place? No, because water is a weak field ligand, which you can keep in mind that knowledge comes from your spectrochemical series. You need to learn that spectrochemical series. So here 3d6 means number of unpaired electrons will be 4 as it is. So you can clearly see that if I fill 3d6, it clearly gives us an idea that the number of unpaired electrons are 4. So number of unpaired electrons are 3 in the first case, number of unpaired electrons are 4 in the second case. If I talk about nickel NH3 whole 6 +2, we'll clearly keep in mind that here, if I talk about the case of nickel, if I talk about this particular case for nickel, you can clearly see that if I talk about the case for NiNH3 whole 6 +2, let me quickly discuss that. So, NiNH3 whole 6 +2 if I talk about. So, here nickel +2 is 3d8 4s0. So, if I fill all these 8 electrons, it will be 1, 2, 3, 4, 5, 6, 7, 8. Now, we all know that if you need to make D2sp3, you need to have at least 2. You need to have actually 2 inner d orbitals empty, which is not the case here. So obviously in such cases, the outer complex will be preferred and you will be getting sp3d2. So 4s, 4p and the remaining part of 4d, those will be involved to make your hybridization sp3d2. So we'll keep in mind, even if I pair here, I'm not going to get inside inner 2 d orbitals empty. So it's going to stay as it is, and we'll keep in mind whenever nickel is making an octahedral complex and it's in +2, we usually get sp3d2 as a hybridization, irrespective of whether ligand is strong or whether it is weak. However, here the case was of strong ligand. Okay, so we got an idea that number of unpaired electrons are 2. Now, so number of unpaired electrons in this particular case is 2. Now, last part, cobalt +3. Now, cobalt +3 is 3d6 and ammonia is a strong field ligand. So, pairing will take place and this 3d6 will look like this. So, here I can clearly see in presence of strong field ligand, my number of unpaired electrons are 0. So in the case of chromium, the number of unpaired electron is 3. In the case of iron complex, the number of unpaired electrons are 4. In the case of nickel, the number of unpaired electrons are 2. And in the case of cobalt, the number of unpaired electrons are 0. So if I match, I can clearly see the answer will be C, D, B, A. So the answer for this particular match the column will be first. Okay, so that was a question from coordination compound, which is an important chapter from your class 12 in organic chemistry. Alright, so let's talk about our next question, which is about chemical kinetics, and it is about complex order question. So it says that the hypothetical reaction, which is P2 plus Q2 gives 2PQ, it follows the mechanism as given below. So you can clearly see that this kind of mechanism is shown here, and they are actually asking us the order for this complex reaction. So we are provided with the fast step, we are provided with the slow step, and again the fast step. How shall we proceed with the order of a complex reactions, my dear students? We'll keep in mind that here the important step whose rate expression we need to write is actually the RDS, which is your slow step. Now, if I write the slow step rate expression first, or the rate law expression first, what I'll be getting? So let's understand the solution for this question. So I'll be writing the rate law expression for this slow step. Let's proceed. So I'll be writing R is equal to K. Let's say that the rate constant for this slow step is K1. So let me write it as K1. Concentration of the reactant P into concentration of the reactant Q2. Now, let's mark it as our first step. Now, we need to keep this in mind that in our final rate expression, we need to ignore here the intermediate. You can clearly see that P is forming here, but P is consumed in the next step, and P is also utilized in third. So P is our intermediate which we need to remove. It's not a part of our final product, neither it was initially present nor it is finally there. So we need to remove intermediate from our final rate law expression. So our target is now to eliminate this P, because we'll keep in mind that P is something which we don't need, because a main reaction, if I talk about, is also not having any P involved. It's P2 and Q2 which is there in the reactant side. So now we'll be taking the help of the fast step. Let me mark the rate constant as K2 for the forward step, and let me mark the rate constant as K3 for the backward movement. Now, if I write the equilibrium constant, let's say that this reaction is at equilibrium, how will I write the equilibrium constant? I'll just be saying that it will be forward rate constant upon backward rate constant. Okay, so I'll be writing it as K2 by K3, and it will be nothing but it will be concentration of the product raised to the power 2 divided by concentration of P2, which is a reactant. Now, if I find the value of P from here, what I'll be getting? P square is coming as K2 by K3 into concentration of P2. Therefore, I can say that from here, concentration of P is coming as square root of K2 by K3 into concentration of P2. Now, finally, I got my value of P. Let me mark it as 2. And now I'll be putting this value of P in my initial RDS rate law expression. So I'll be substituting this value of P here. When I do this substitution, what I'll be getting? So finally, I can write that rate is coming as K1. P value will be K2 by K3 into P2. This is the final value of P I have put. Okay, this is the final value of P I have put, and now into Q2. Now, I know that, all these rate constants together, they are all constants. So, I can put it as a new constant, which is, let's say, K, just to simplify. So, finally, what I am getting here is, I am having here square root. K2 by K3 also I was having square root of it. You can clearly see it is K2 by K3, P2 raised to the power half. So raised to the power half, raised to the power half. And this entire thing, K1 into square root of K2 by K3 is a new constant, let's say K. So finally I can say my rate expression from here is, rate is K P2 raised to the power half Q2 raised to the power 1. And from this final rate law expression, I can conclude that my order for this particular complex reaction will be summation of the powers of these particular reactant concentration, which comes out to be 3 by 2. So I'll be saying the order for this complex reaction will be 1.5. So that will be our answer for this particular question. I hope everybody has got till here. Now, okay, so let's discuss our next question, and this particular concept is about chemical kinetics. That's first order question, because this question is about radioactivity. So any such question related to radioactivity, my dear students, is first order. Now let's understand. So they are saying that the half-life for radioactive decay is 2000 years. If the concentration after 8000 years is 0.02 molar, then the initial concentration we need to find. We will be using the integrated rate law expression for the first order, and using that we will actually be getting the initial concentration. Okay, so if I talk about the integrated rate law expression for our first order, before that, if I talk about, let's understand, it is rate constant equal to 2.303 divided by time log initial concentration divided by concentration at time t. Now, they have not given us the rate constant, everybody. So they are actually, giving us a hint that you need to make use of the half-life which is provided here. So there again, it should click in your mind that the half-life for first order expression is that K can be written as 2.303 log 2 divided by T half. So I can substitute my rate constant in this particular way. I can also write ln 2 by T half, but it's better we use 2.303 log 2 by T half, because that way 2.303 will get cancelled out by this 2.303. So let me put the value of K. So I'll be getting 2.303 log 2. The value of T half which is given in the question is 2000 here. So I'll be putting that 2000 equal to 2.303. Now, the time which they are talking about when the concentration becomes 0.02 is 8000. So I'll be putting that 8000 log. Initial concentration is A0. Final concentration is 0.02. So final concentration is 0.02. Now 2.303 cancels out. 2000, 8000 cancels out. I'll take this 4 on the left side. What I'll be getting? 4 log 2. 4 log 2 I can write as log 2 raised to the power 4. And I'm equating it to log A0 divided by 0.02. Now, if I compare both these sides and I just remove this log part, what I get from here? 2 raised to the power 4 equal to A0 divided by 0.02. Now, if I solve this particular part, I'm getting A0 as 16 into 0.02, which comes out as 0.32 molar. Okay, so my initial concentration is 0.32 molar, and before radioactive decay, it was 0.32 molar, and after radioactive decay, it has become 0.02 molar. So this is a question about first order, and the answer for this particular question will be second option, which is 0.32 molar. So initially my concentration was high. After decay, which is following a first order mechanism, it becomes 0.02 molar. So that was your question from chemical kinetics, and first order is an important concept from chemical kinetics. Okay. Alright, so let's discuss question number 5. This particular question is regarding benzaldehyde and benzaldehyde undergoing this particular reaction. You can clearly see that they are asking us the product formed from the following reaction sequence. Okay, so you can clearly see that first cyanohydrin formation is taking place. In the step 2, they have mentioned that we are doing acid hydrolysis, acid catalyzed hydrolysis. Since they have not mentioned complete or partial, we have to take it as complete hydrolysis. And lastly, what reaction is this? This is soda lime decarboxylation. So this is a concept which is coming from your aldehyde chapter, then the hydrolysis part is coming from your carboxylic acid chapter, and then the soda lime decarboxylation is involved in your aldehyde ketone carboxylic acid chapter part also, and in your alkane part also. When we prepare alkanes, that time also we study soda lime decarboxylation. Okay, so if I solve this particular question, the step 1 which we are having is that we are provided with benzaldehyde, and we know that whenever cyanohydrin formation takes place, it happens in basic medium. So cyanide first attack this polar bond of CO, because this is a polar bond. Attack will take place like this, followed by we are giving H plus. So what we'll be getting in this particular part? We'll be getting something like this, that we'll be getting here OH finally, because we have given H plus after cyanide attack, and we'll also be getting this cyanide finally getting connected. Okay, now after this particular step, my dear students, we need to keep in mind that we are provided with H3O positive. Now when I talk about this H3O positive here which is mentioned, we'll keep in mind that this is your cyanide which undergoes complete hydrolysis. And when cyanide undergoes complete hydrolysis, it gives us the formation of carboxylic acid. Obviously, the hint is there in the question itself that in the last step, if they are giving us soda lime decarboxylation, so you need to take a hint from there that definitely carboxylic acid is forming. So this is a complete hydrolysis, my dear students. If they are not mentioning the partial word, then you will not make the amide. You have to do the complete hydrolysis of cyanide. And when we do the complete hydrolysis of cyanide, it is the carboxylic acid formation which takes place. It's simple way to remember this step, that whenever we are having this cyanide, you just remember it like this, that you are providing water 3 times. So when I break this bond, I am giving OH, H. I am breaking this bond, I am giving OH, H. I am breaking this bond, OH, H. Now from this side we are getting ammonia, that's fine, that's not a concern. But from this side if you see, we are getting C, OH, OH and OH. And when I remove water, because you know on one carbon if there is more than 2 OH, it's unstable. So when you remove water, finally what you get is this kind of functional group which I have written here. So that's what I'm saying, that cyanide's complete hydrolysis gives you carboxylic acid. When you do now soda lime decarboxylation, which is NaOH plus CaO combination. Now you'll keep in mind that this particular soda lime decarboxylation when we are doing it in presence of what? So soda, that is caustic soda, and quicklime. So soda lime decarboxylation. Here you can clearly see what is mentioned in this particular question. It is in 3:1 ratio. So NaOH is in higher quantity, and if I talk about quicklime, that is just added to keep my NaOH dry because it is hygroscopic in nature. So we'll keep in mind that when we treat our COOH part with NaOH plus CaO, we'll ultimately be getting what? CHOH, and we'll just be left with this extra H. So this is nothing but this is a 1 degree alcohol which we are getting here. So if I see where the answer, you can quickly see that the answer for this particular question will be second. So that's the answer, which is benzyl alcohol. We'll keep in mind that we are removing actually CO2 in the form of Na2CO3, and That way, one of the carbon is less in my final answer. You can clearly see that we had an extra carbon here in the form of carboxylic acid. When I treated it with this soda lime, that resulted in removal of this carbon dioxide part, and that carbon dioxide goes in the form of Na2CO3. Okay, moving ahead, our answer we have got, which is second. Let's talk about the next question. Now, you can clearly see in this particular question that this match the column is provided about the structural isomerism part from coordination compounds. So, if I talk about the very first step, the very first one, if I see, the difference is the way ligands are connected to the central metal. One is nitrito N, one is nitrito O, and whenever there is a difference in how there is a linkage of these ligands, such an example is of linkage isomerism. Next, if you see the second option, you can see that there are two brackets which is provided. And whenever there are two such brackets, means your cationic part and anionic part, if both are in the complex forms, then the isomerism which they usually show because of the interchange of the ligands, you can clearly see here with chromium we have ammonia, here with cobalt we have cyanide. But then here you can see that chromium is now with cyanide and not with ammonia anymore. So there is an interchange of ligands between these complex parts, and such an example is therefore of coordination isomerism. Next, if we see, so we can clearly see here that sulfate and bromine interchange their places. So if I ionize this particular coordination compound, I am getting bromine as my counter ion here. But if I ionize this as my compound, I'll be getting sulfate as my counter ion. So whenever you see that on ionization you are getting different ions, then such a isomers are examples of ionization isomerism. Next we have, if you can see that here my water, in fact all the waters are acting as ligands, they're connected with chromium which is in +3. But here one of my water has gone as water of crystallization. So when water is playing a dual role, then such isomers are example of hydrate or solvation or solvate isomerism. So finally, if I see, for the first one we have third. So third, second, first, fourth. Third, second and first and fourth. Third, second, first and fourth. So the answer for this particular question will be third. I hope everybody understood till here. Now, alright students, so now let's talk about our question number 7, which is from D and F block elements. Now this particular question says that we have been provided with statement based questions, students. So you very well know that as far as your previous year goes, we have this statement based questions which are coming, and match the columns also were there a part of in the previous year. So we have to be good with statement based questions. We have to read properly. And this particular question, what it says, let's see. So statement 1 says that chromium +2 is oxidizing and Mn +3 is reducing in nature. So when we are saying oxidizing, means we are talking about its oxidizing power, means we are talking about that it's an oxidizing agent. And here we are seeing that manganese +3 is a reducing agent. So it is opposite actually they have written. Manganese would not love to oxidize itself and reduce others. Manganese would actually reduce, it will try to reduce itself, because when it try to reduce itself, then only it become a D5 configuration where it is happy. So it is not reducing in nature, it is oxidizing in nature. And when I talk about chromium +2 is oxidizing agent, means it wants to reduce itself. That's not true. Actually, chromium +2 wants to oxidize itself, because when it is in +3 state, it is a D3 configuration. And if you go by the concept of T2G3, it's quite a stable configuration. If suppose chromium +3 is making an octahedral complex, we'll keep in mind that all these three unpaired electrons are going to these lower energy orbitals rather than higher energy Eg orbitals. So you are going to this lower energy T2G orbital, which is a stable state. So chromium plus 2 is not oxidizing. In fact, chromium plus 2 is reducing. Now, statement 2, what it says, scandium plus 3 compounds are repelled by applied magnetic field. So we know that by checking the number of unpaired electrons, we can judge the magnetic behavior of an ion. And if you see here, scandium plus 3, it is having a 3d0 configuration. Means obviously it will not be magnetic in nature. So this statement is absolutely right. So first statement is incorrect, whereas the second statement is correct. So the answer for question number 7 will be 4th. Alright students, let's talk about question number 8, which is a question from your solid state, which is actually discussing this concept of FCC and BCC and their density and the relation of side with radius, and that's why it again becomes a multi-concept question. So let's discuss what it says. It says that iron exhibits BCC structure at room temperature, but they are saying it changes its behavior above 900 degrees Celsius and it transforms to FCC. Now they are asking us the ratio of density of iron at room temperature to that at 900 degrees Celsius. Also they are saying that assume that the molar mass, the atomic radii of iron remains constant. So they are giving us some assumptions which we need to follow. So these are your options. Let's check that we are actually getting this answer or not. So we'll keep in mind that if we solve this particular question now, we know that density, below 900 degree when it was BCC divided by when it is above 900, this ratio they are asking us. And we know that density is Zm by A cube Na, where Z is your effective number of atoms within that unit cell, M is molar mass of iron, obviously we need to keep, A is side of the cube, and Na is Avogadro's constant, divided by Zm upon A cube Na. But this particular Z value and A value, this particular Z value and this A value, you have to be clear with that. What things you need to be clear? That Z value for BCC is 2, Z value for FCC is 4. Apart from that, the relation of A with side is obviously different for BCC and for FCC. So we know that for BCC case, the relation of side with radius is √3a 4r. Okay. And they have mentioned that radius is same. So in terms of radius, we need to solve this question. So the r value, if I talk about the A value in terms of r, it will be 4r by √3. Similarly, for FCC, if I talk about, the relation is √2a equal to 4r. So A value comes out to be 2√2r. So we'll be using both these relations in order to solve this question. Now, let's solve this question. Z value for BCC is 2. Molar mass I'll keep as M because it will cancel out. A value is how much? 4r by √3 raised to the power 3 Na divided by 4 is the value for FCC. Relation is 2√2r cube Na. Now, many things are getting cancelled out. My r cube, Na, molar mass, r cube again. Now, remaining things we need to solve, right? So, what I'm getting from here is 2 by 1 divided by 64 by 3√3. This is the part I'm getting from the top. Okay, 2 by 1 divided by 64 upon √3 cube is 3√3. Then from the denominator part, I'm getting 4 divided by 2 cube and then this √2 cube. So it will be 8 into 2√2. Okay, so now if I gather all these values, I'm directly getting 3√3 by 4 root 2. So when we'll be solving this particular part, we'll be getting 3 root 3 divided by 4 root 2. If we see any such option which is mentioned here, we can see this particular option, which is our option number C. So 3 root 3 divided by 4 root 2, we'll keep in mind that here what is absolutely important is the Z value, which is different, and the relation between A and R. Okay, moving ahead, let's talk about our next question. Okay, so students, let's talk about question number 9. This particular question says that which of the following pairs of compound is isoelectronic and isostructural? So if you see here, we are provided with options like TeI2, we are provided with XeF2 in option number 1. Here we are provided with IBr2 minus XeF2. Here we are provided with IF3 and XeF2, and here we are provided with BCl2 and XeF2. Now keep in mind, for a species to be called as isoelectronic, we'll keep in mind one fact. What fact we'll keep in mind? That for a species to be called as isoelectronic, you need to have same number of valence electrons, you need to be having same hybridization, and also you need to have same number of atoms. When is this rule I am telling you? For polyatomic species. For polyatomic species, I am telling you. If you are having a monoatomic ion, you can just say that, ma'am, total number of electrons have to be same. Like Na plus and F minus, they are isoelectronic species. Okay. So here, I can see that total number of atoms are same in this particular case, that is 3 and 3. Valence electrons, if I see, that is 8 plus 7 plus 7, that is also same, which is 22. 8 plus 7 plus 7, that is again 22. So that is also coming same here. And if I talk about hybridization, then XeF2, if I talk about, it is sp3d and it is linear in shape. And if I talk about IBr2 minus, which is very much similar to I3 minus, it is again linear and it is also sp3d. So these species are having same valence electron, same hybridization, and you can see same number of atoms as well. So our answer for this particular question will be second, you can clearly understand. Here you can clearly see there is a difference in hybridization and you will come across a difference in valence electrons also. Here in this particular case, you will come across a difference in valence electron because this is 16th group and this is 18th group. And here also you can clearly see a difference in valence electron and in difference in number of atoms as well. So the answer for this particular question will be second. Alright students, let's discuss question number 10, which is a question from metallurgy. The part which is mentioned here is of refining of metals. You can clearly see that when I talk about cupellation, now cupellation is a particular technique which is used for the refining of silver from the impurities like lead. So we'll keep in mind that the basic principle is that the metal is not forming oxide because it's not having that much affinity, but the impurity is having more affinity than silver and thus lead will come out in the form of oxide. Silver will not be forming an oxide and will stay there. So cupellation is a technique for purification of silver. Now zone refining is next. Zone refining is generally used to obtain pure metals, especially semiconductors, especially metals of group 14 and 13. So zone refining is a technique where a principle goes that impurities are more soluble in the melt, right? So zone refining will be for this group 14 element, which is germanium. Then we have Van-Arkel process. Now students, Van-Arkel process is a vapor phase refining method for zirconium and titanium. So answer will be D, and distillation is usually for those metals which have low boiling point than their impurities like zinc, cadmium, mercury. You can learn that distillation can be used for all these pseudo transition elements. So here we'll be having an answer which is C. So if I match, what I'll get is BADC. So BA and then DC. So the answer for this particular question will be 4th. Now, alright students, so now let's discuss question 11, which is from chemistry in everyday life. You need to keep in mind that this chapter also plays a great role, because here you just need to, memorize the drugs, to which classification of drugs they belong to, and therefore these are the questions from which you can encash the marks easily. Okay, so this question is again a match the column. You can see here that they are discussing anti-fertility drug, tranquilizer, antihistamine and antibiotics. So anti-fertility drug, if I talk about, it is norethindrone. We also have novestrol as our anti-fertility drug. Then tranquilizer, we'll keep in mind that tranquilizers are usually used, to get over stress. They are hypnotic drugs as well to get over anxiety. So tranquilizer, meprobamate. Then we have antihistamine, which is here Seldane, if I talk about. An antibiotic which can be broad spectrum, narrow spectrum or limited spectrum. Here the antibiotic is just like we have penicillin, ampicillin. So here I can clearly see it's quite direct. So I can match it, which is 1st, 2nd, 3rd and 4th. So the answer for this particular question will be 4th. We'll keep in mind that there are a lot of tranquilizers, and tranquilizers are quite important, whether it is, tranquilizers like meprobamate or tranquilizers like Equanil, tranquilizers like chlordiazepoxide, tranquilizers like iproniazid. So keep this thing in mind that you put all the tranquilizers at one place. Alright students, let's discuss question number 12, which says that the correct order in aqueous medium of basic strength in case of methyl substituted amines is. So when I talk about methyl substituted amines, you are provided with the options. We'll clearly keep in mind that in aqueous medium, the basic strength depends on inductive effect, it depends on steric hindrance, and it depends on solvation factor. If we combine all these three factors and experimentally we come up with this particular order, which is your 2 degree methylamine comes first, then your 1 degree, then your 3 degree and then ammonia, which is the case with option number 3rd. So 2 degree 1, then 1 degree, then 3 degree and then ammonia. We'll keep in mind this particular order 230. If it is the case with ethylamines, then the answer is 2, 3, 1 and then ammonia. So keep this in mind, 231 is the order for ethylamines and 213 is the order for methylamines. We'll keep that in mind because methyl is a smaller group. We'll keep in mind that the number is 213. Ethyl is a bigger group, so the number is 231. So the answer for this particular question is 3rd, based on the 3 factors which affect the basic strength in aqueous medium. Now, alright students, let's discuss question number 13, which says that match the following row 1 with those of row 2nd. Before we see the row 2nd, which is this particular thing, if I talk about this row 13, this is what it is mentioned. You need to just match those compounds with these particular row 2nd options. So if I see the diagram, you can clearly see here that this particular is pyranose and it is for beta D glucose. We can say beta D glucopyranose. If you see this particular part, it is alpha part of glucose. If you see this particular part where OH will be on left side and CH2OH on the other side, so that way if you see, this is alpha fructose and this is beta fructose. So based on that, if we match, it will be beta alpha alpha beta. Okay, let's check. So for the first one, if I talk about alpha D glucose, so this will be our first one. Then we had beta glucose, that will be our second one. You can clearly see here. This was a beta one, then we have alpha. So beta alpha alpha beta. Okay. So if I talk about, this will be beta was the first one. So this will be A, then alpha, that will be a second one, and then we had again alpha, that will be a third one, and then we had beta, which will be a fourth one. So our answer will be clearly, if I talk about, it will be, for the first one it will be fourth, for the second one it's gonna be third. So fourth, third, and then first, and then second. So that's gonna be our answer. That will be answer 2, because for the first one the fourth one is matching, which you cannot see anywhere else apart from option 2. So that's the question from biomolecules. In biomolecules, you need to keep in mind all these structures, and also about reducing, non-reducing, about sucrose structure as well. Alright students, let's talk about question 14, which is about acidic strength comparison. Here you have been provided with the question, which is the increasing order of the pK for the following phenols is. So we'll keep in mind that the acidic strength is directly proportional to -I -R groups, because these groups stabilize your conjugate base. So we can clearly see here that maximum -I -R group, which is nitro groups, are present in your option A. Followed by that, if I compare methyl is a +I +H group. So it's not going to be a supporter. So that we'll place in the last. So C option, where it is last. In fact, these two are bad acids, because they're saying increasing order of pK values, means increasing order of pK, these two have highest pK values and they are bad acids, and highest will be A option. So A is there in front of both. So we need to check just one more. So here if I compare now phenol is not having any supporter group. So second last in terms of acidic strength will be D, which is the case here also and here also. Now next confusion which we have is between B and E. Okay, so B and E here also, B and E here also, that's your confusion. But we'll keep in mind that nitro is more of an electron withdrawing group, both in terms of its power of -I and -M. So we'll keep in mind that acidic strength will be higher for the case of 4-nitrophenol rather than 3-chlorophenol. So therefore pK value will be higher for the E part. So E will be coming later, and that's why your answer for this particular question will be D option. Alright students, now we have a question number 15, which is from SN1 reaction, and that is from your haloalkane and haloarene chapter. So you can clearly see here that they have asked the decreasing order towards SN1 reaction, and we'll keep in mind that in SN1 reaction, which is a two-step process, the first step is towards carbocation stability. So when I remove the chlorine, I'm getting carbocation formation in each case. And I need to see what these groups are, helping the carbocation or they're not helping. So nitro is -I -R, methoxy is -I and it is +R, chlorine is +R -I, and there is no such group which is attached here. So obviously, if I talk about, I need to keep in mind that SN1 is directly proportional to stability of carbocation, and +M groups support the SN1 process. And I can see that here methoxy by +M is supporting. Okay, you can see here also, but here you know that in the case of halogens, inductive part dominate over mesomeric. We keep that thing in mind. So overall, the effect of chlorine is deactivating. Overall impact is deactivating. Here if I see, overall impact of nitro by -I and -R is deactivating, and here no group is there. So best for SN1 is option number 2. Okay, so if I finally mention now, what we'll be getting? So if you see finally, you can clearly see best is option number 2, which is +M. Followed by that, if you see, this is also deactivating, this is also deactivating. So next will be D. So after B, we have D. Then this is more deactivating because of -I -M. But this is slightly less deactivating. So we'll be having B, D, then C, and then A. So B, D, C, A, that will be our correct answer for this particular question number 15. Alright students, so that will be it. We discussed 15 questions from chemistry. For the other subject videos, the link for that will be in the description of the entire playlist of the series. Thank you.